Hello, welcome back. In the previous lecture, we discussed a little bit about the seismic zones around India, and we talked about that how uh, most of the parts of India, either it is in the continental mainland part or maybe around the coastline, most of them are vulnerable to earthquake and tsunami, and more precisely the Himalayan front or the region adjoining the Himalayas and within Himalaya is extremely vulnerable to large magnitude earthquakes. And that day we were talking about that we have a couple of large magnitude earthquakes which we experienced in Himalayas starting from 1885 to 2015 Gorkha earthquake, which was the recent one last year, magnitude 7.8. Now, before moving ahead, just briefly I would like to mention that whatever the records we see here, okay, or the information we see here is not the complete one, okay, because we don't have uh, the uh, the complete historical records from this region, and also what we are doing at IIT Kanpur along with other teams in India, that we are trying to identify the paleo earthquakes, signatures of paleo earthquakes in Himalaya, which are preserved within sediments and on the surface. So, the aim is to complete the catalog of this ancient earthquakes, which will eventually is extremely helpful for proper seismic hazard assessment of any region. So, that is what we are doing over here. Now, moving ahead, when we talked about the earthquakes and all that, based on the whatever the earthquake data is available from different parts of India, the zonation map has been prepared, and this zonation map has been divided into 4 zones starting from 2 to 5, where the most of the red portions which you see here, okay, are all fall in zone 5, which are extremely vulnerable and will have very high seismic shaking during major earthquakes. Okay. So, if you look at, we have here that is the Andaman here, and this portion whole is of the Himalaya, and then we have the Kutch here. Okay. And now Kutch comes here because of the earthquakes which are been listed here. So, this is these are the areas which are extremely vulnerable to earthquakes in future also. Okay. If you look at, so I will briefly talk about some faults in Himalayas. If you look at in the Himalayan region, mainly what we have is that the initially, when if you recall the previous course, we talked about that the Indian plate subducted below the Eurasian plate, and finally what we are having, that was between the oceanic plate or the portion of the oceanic plate which was ahead of so if you look at here, well, I'll just put a sketch here. Okay. So, we had an the continental plate and we have the oceanic plate here, which subducted below the continental plate of Eurasian. This is Eurasian plate and this is your Indian plate, we can say. Okay. So, this subducted, so this is an oceanic plate, and then we are having this one is your continental plate. But now what is happening, when it came close to the continental plate of the Eurasian side. Okay. So, now what we have is just the collision which is going on, okay, and that is resulting into the formation of Himalaya. So, we are no more having the oceanic plate going down, okay. But since it subducted below, so we have still that contact exists, okay, and which has been shown here. So, we are having what we call, it is in the form of the detachment, okay. So, we have this detachment going on below the Eurasian plate, and what we see is the Himalayas are coming up, okay. So, Himalaya is not in single mountain, but it is a chain of mountains. So we have the Himadris or higher Himalayas, then we are having lesser Himalayas, and then we have Shivaliks, that is the we call sub Himalayas at present. Okay. So the elevation also, if you look at, we have the elevation which reduces from 7,000 meters, and the highest is around 8,000 meters, that is of the your Everest. Okay. And then it reduces to 600 to 2,500 meters, and finally to around 600 to 1,500 meters. Okay. So this is what we see, and then this all mountain chains are been separated, or we can say bounded to their south by major fault systems. Okay. So one is your what we call is the MCT. This is a main central thrust, and then we are having MBT. Now MCT is separating the lesser Himalayas from the higher Himalayas, and then we have MBT fault system which separates the lesser Himalayas from the sub Himalayas, and finally we are having the HFF, or we say HFT. Okay. This is your HFF, or we say HFT, Himalayan frontal thrust. This Himalayan frontal thrust mark the boundary between the lesser sub Himalayas and the Indo-Gangetic plain. So this portion is our Indo-Gangetic plain. So we have this, and the Himalayan frontal thrust is the present day plate boundary between the Eurasian plate and the Indian plate. So what it has been observed over the time now within the Himalayas, that most of the earthquakes are occurring between the main boundary thrust and the main central thrust, beneath those two faults. Okay. So we have the clustering of the earthquakes which are triggering mainly between main boundary thrust and MCT, main central thrust, and then the deformation has been taken up by the younger faults in the foreland side. So this is what I was talking about, the boundary between the Indo-Gangetic plain and the Himalayan frontal thrust. This is sub Himalayas, and then we are having MBT, boundary between the sub Himalayas and the lesser Himalayas, and MCT is between the lesser Himalayas and higher Himalayas. Now we have some records of the historical events which have been experienced in Himalayas. So which starts right from AD 25. This was in Takshashila earthquake, and then we have a couple of large magnitude earthquakes which are marked by the yellow areas. Now these yellow areas are the probable rupture areas, okay, where the rupture extended along the fault lines. Okay. So this is one is 1555 is of Kashmir, and then we are having 1905 of Kangra, then we are having 1803 in Nainital region, then we are having another one which extend quite a bit, and which is 1505 earthquake, and then we are having 1833, and then we are having 1934, and further this side if you go towards Assam we are having 1950, which is not in this map. Okay. So we have some records, but this is again we can say that there is not an complete record from the Himalayan region. Some studies which maybe I will if I have time I will discuss it separately, which have been conducted mainly based on the geological and geomorphological studies, which revealed that there are paleo earthquakes which have occurred, like for example in 1255 this was a major one, AD 1255, and then near Nepal there was another earthquake which was in like AD 1100, and then from the portion which is of the Himalaya in India we have a couple of earthquakes which have occurred in like this is listed here, which is not clear. Maybe we will try to put it on slide clearly. This is 1294 or so, and then we are having 1400 event. Okay. So, there are a couple of earthquakes which have been listed again from Chandigarh area. We have been able to identify the event around 1500 to 1400 to 1500 AD, and then we are having again close to this Pathankot regions. We are having again an earthquake which occurred during 1500 AD. So, and also our recent findings have suggested that this 1905 earthquake, which was the major earthquake, killed almost like 20,000 people at that time in 1905, is again was triggered within the valley. So, there was a fault which we have recently identified and named as Kangra Valley fault, which was responsible for producing the 1905 earthquake. Okay. And this faults run for almost like 60 to 70 kilometers, and it is having a motion which we say right lateral strike slip motion. Okay. So, again within thrust environment or the compressional tectonic environment, where usually we expect to have mainly thrust faults and reverse faults, but at some places we are also seeing or we are also observing the strike slip moment, and this is mainly because of the oblique convergence in some regions, okay, within the Himalayan domain. So, we have coming up with a lot of data from what we call based on the paleoseismic studies. So, we have been able to locate and identify the signature of paleo earthquakes. Okay. And let me share here one more thing, that our recent investigation from this area particularly, where we are having an overlap of the 1803 and then we are having the 1505 rupture. Okay. So, from this region we have been able to pick up the signatures of AD 1803 and 1505 earthquake. This we recently published in one of the journal, where we talk about that near Ramnagar area. This is a famous area where most of the people go. This is an area where we are having corporate park. So, there we have been able to identify the signatures of these two earthquakes which occurred during 1803 and 1505. Let us move ahead and see what happened. There was a deadly earthquake in 2010. This is what is the example of the destruction, and the photograph which is showing massive destruction and killing almost like 2 lakh, more than 2 lakh people in that region. Okay. It's a Haiti earthquake of 2010. Then these are some old pictures which were been taken from Dharamshala. Total damage resulted because of your 1905 Kangra earthquake. So, this is an example of that. So, we have more. There was a massive damage in that area. Now, total damage, I am sorry, this is 1905 event of Kangra, which was magnitude 7.8. This we have, I think we have shown a couple of pictures. This is from Bhuj 2001, Bhuj earthquake. This is again from Bhuj. So, we experienced total damage. Now, what are earthquakes actually? Let us have a very quick discussion on that part. What are earthquakes? In previous slides and lectures we have talked about that it is a sudden release of the energy stored within the earth crust, okay, because of the ongoing tectonic deformation. And the manifestation of those displacements on the surface are termed as active faults. And this is what is one of the famous fault line in US, America, which is termed as San Andreas fault system. So, this is the trace of that. If you see from here, this is, and then what we are able to see here is that this fault has produced many earthquake in the past, and there is a likelihood of having an earthquake in future also. So, this is a live fault, or we can say the active fault, which is having an motion of a right lateral slip. Okay. This is a right lateral strike slip fault, and this portion what you see here is the fault scarp, and the streams which are flowing across this fault are getting offset, okay, or they are deflected along the motion of the fault. Another best example of the picture of that. Okay. So, we have the strike slip motion here, right lateral, this is your fault scarp, and the fault trace is over here. And if you carefully see the streams which are flowing from here are getting deflected along the fault. Okay. So, this is one, this is another one. Okay. So, if you look at what is the best way to understand and to know that whether this fault has moved multiple times or not, if you look at this stream, okay, this is showing larger displacement as compared to this one. So, this means that this stream was offsetted maybe during one or two earthquakes, but this is showing a cumulative displacement in this particular portion of the fault. Okay. So, that also gives an idea that this fault has been moving continuously over the time and resulted into many earthquakes in the past, and has there is a likelihood of having an earthquake in future also. Now, this is one of the very nice example which has been given by US Geological Survey, where what they explained is that you take up both the hands, okay, and try to press it towards each other and try to move. Okay. So, there is a friction which has been developed in between your two hands, okay, and when you are moving, of course, you are putting a lot of pressure on it and then trying to move, okay, and when it slips suddenly, you will get a jerk over here, okay, or some vibrations will be there on your in your hand, okay, and that vibration is what we call the earthquake. So, similarly, two rock masses are moving, are under compression, or maybe tectonic, because of the tectonic forces, okay, and there are pressure or the strain is building up, and when it moves or the slip, okay, it will result into the vibrations. So, sudden release of the energy which has been stored. So, as we have been talking about, that if you keep on increasing the stress, strain will develop, and finally, you will have the fracturing. Okay. So, plastic deformation, ductile, and then you are having the fracturing. Okay. There is another example which has been given, because on the earth's surface we do not see only one single fault line, there are multiple fault lines. Okay. So, if you look at like what we were talking about, the Himalayan frontal thrust and all that. Okay. So, if you look at this one here, we are having multiple fault lines. These are all black lines which have been shown in Himalayas or mapped in Himalayas are the location of preliminarily active faults. Okay. So, we have multiple fault lines which you will come across in any tectonically deformed region. Okay. So, this is an example which has been given, that if you take a set of a playing card and try to press against each other and move in any particular direction, okay, then what will happen, that in the playing cards, the contact between each playing cards, you consider that as an weak zones, okay, which will move at different rate. It will not move at the equal rate, it will move at the different rate, and that is what we call the slip rate. Okay. Slip rate is we measure or talk in terms of per year. So, slip rate of each fault or the contact between the each rock blocks will be different. So, this it is important to know the slip rates, that how this faults are slipping. Okay. If slip rate is higher, then you are accumulating more strain. That means you will have the recurrence of an earthquake will be very short. Okay. So, you will have very quick earthquakes in terms of the time. So, this is extremely important, and that what we have been doing in Himalayas particularly, that to identify that which fault, if those are active faults, which fault out of them is moving faster. That will tell us that what is the hazard posed by that particular fault in that region. Okay. So, if slip is faster, strain will be more in that area. So, we need to identify the potential regions or the areas where we are having higher strain accumulation. So, this is an example where they suggested that if the Pacific plate and the North American plate, if they are moving, okay, what will happen, and they will have multiple fault lines over here. Okay. So, this is the region where we are having in this particular part, where we are having the Pacific plate. This is the Pacific plate, and subducting below or slipping along the North American plate. Now, earthquake forecasting and prediction. As I told in the previous lecture, that it is not very much possible to forecast the earthquakes, but people have tried looking at the precursory events and have predicted a few earthquakes. So, forecasting identifies both earthquake prone areas and man-made structures that are specially vulnerable to damage from shaking. Okay. Earthquake prediction refers to attempts to estimate precisely when the next earthquake on a particular fault is likely to occur. So, this prediction is what I would say that is a part of the studies what we are doing, paleoseismic studies. Okay. So, at least we will be able to talk about that when the next earthquake on which particular fault it will occur. Okay. So, this is very important. So, those the studies which we are doing is, of course, we are looking at the signatures of earthquakes which took place in last 10,000 years. Okay. But the recent development what we have now we are doing is also based on the GPS measurements. Okay. So, we have the permanent GPS stations put across the faults and try to measure that, because GPS 24/7 it will collect the coordinates. Okay. And since we understand that there is a shift. Okay. So, since we know that there will be a shift, there is a velocity, at particular velocity the plates are moving. So, we can precisely monitor those movements along within the earth crust. Okay. Now, second part of the earthquake prediction, if we take, okay, earthquake forecasting is based largely on the elastic rebound theory and plate tectonics. Okay. The elastic rebound theory suggests that if fault surfaces do not slip easily past one another, okay, so that means they are like locked. Okay, and they are storing the energy within them. Okay. So, what happens, the energy will be stored in the elastically deformed rocks. Okay. So, this is what is happening along the fault line. So, it will not keep on slipping, but it is locked and it will keep on accumulating the energy. Okay. And since it will keep on accumulating the energy, there will be some deformation, which is what we call the elastic deformation will be there in the rocks. Okay. And this can be captured or recorded by GPS measurements. Okay. So, currently seismologists use plate tectonic motion and global positioning system GPS. Okay. Measurements, so GPS measurements to monitor the accumulation of strain within the near the active fault. So, for example, if you are having an active fault which is running here, okay, if I say this is an active fault line, then you will put a GPS here. Okay, this is what I am talking about, the permanent GPS, and another GPS here. Okay, so this will keep on monitoring. So, if the motion is like this, okay, that is within, this is in compression, then there will be movement which has been seen, this coordinates of this two GPS will change. Okay. And suppose if you are having, so this they will be, so over the time this, for example, the one GPS is located here, I will just put the point here, and then, so if you are having one GPS here, another GPS here, so over the time what will happen, the GPS will move towards each other because this is in under compression. So, this will be another position, new position of the GPS. So, there will be in relative motion which can be measured. Okay. But suppose there is an strike slip motion. Okay. So, one plate is moving or the fault side is moving like this or in the other direction, then the GPS over here will move, for example, over here, and then another one will be somewhere over here. Okay. So, you can measure the movement of the along the fault line. Okay. And the deformation can be measured. So, this is extremely important that in current situation with the advancement of science, we have the GPS system which can measure the ongoing deformation of the active faults. I will stop here and will continue in the next lecture. Thank you so much.